Welcome back. So we are in the next lecture of Fundamental of Electronics. We will discuss here the concept of operational amplifiers. The outline goes like this. First, we will see what are operational amplifiers, the difference between idle and practical op-amps, the input modes and the parameters which are associated with the operational amplifiers, what is negative feedback, and the configurations of op-amp in the positive and negative mode, the impedance effect, the bias current and the offset voltages, the frequency response of the op-amp in terms of the magnitude and the phase, the practical consideration that we do, and the conclusion. So operational amplifier, the short form we say to be op-amp, is basically a high gain electronic voltage amplifier with a differential input and a single-ended output. So when we require the high gain for amplifier, we prefer operational amplifier. The input that we give is in the form of differential input because you will have two terminals, and the difference of the voltage at the two input terminal will give you the differential input, and we will get only one single-ended output at the output terminal of this op-amp. So originally, the op-amp were used for mathematical operation in the form of addition, subtraction, integration, or differentiation. Nowadays, in the modern op-amps are basically the linear integrated circuit, which are basically the ICs. They operate with low DC supply voltage. So the input is basically DC and it is of very small magnitude. They are reliable as well as cost effective. Some of the applications of the op-amp is in the area of signal amplification, the filtering, analog computing, and many more such application in electronic principles. When we talk about the symbol and the packages associated with op-amp, we see there are two input terminal for the op-amp. The negative sign indicate the inverting input and the positive sign indicate the non-inverting input, and you will have only one output. So you have basically two input terminal. One is negative and positive. Negative stands for the inverting input and positive goes with non-inverting input. You will get only one output. So whatever the input we are giving will be differential in nature between the inverting and non-inverting terminal. So here the standard op-amp symbol, we will be having the input terminal, the output terminal, and the supply, which is having plus V and minus V. So typically these op-amps are powered by dual DC supplies of plus V and minus V as a source, and or the single supply with the other end grounded. Some of the common IC packages which are the dual inline package, the surface mount technology. So these devices of op-amp are used in the laboratory for experimental purpose, also available in the market in the form of dual inline and surface mount op-amp packages. The historical context goes with 1947 when the concept of op-amp was proposed as analog building blocks. Then the early op-amp were used in the form of vacuum tubes for the high voltage application. It was in 1964 when the first IC op-amp was developed by Fairchild Semiconductor and they designated it to be 702. Later development by the Fairchild, we get 709 and 741. These are industry standard op-amp. Modern op-amp benefit from the IC technology. They are compact, efficient, and versatile. When we talk about the characteristic of op-amp in the idle condition, and then we will discuss the practical condition. So idle condition, the voltage gain will be infinite under the open loop condition. The bandwidth will be infinite, so it will amplify all frequencies equally. The input impedance is infinite. It means no input current is required to drive the amplifier. Zero output impedance, so it is an idle voltage source. There are no unwanted signal in the form of noise. So this is the idle op-amp circuit. You can see here the input impedance is treated to be infinite. The output impedance is zero. The voltage gain is infinite. On the other hand, the practical op-amp will have certain values of these input impedance, output impedance, the voltage gain, and the signal will be corrupted by noise signal. So practically the op-amp open loop voltage gain is very high in the range of 10 to the power 5 to 10 to the power 6. Input impedance is also very high, 10 to the power 6 to 10 to the power 12 ohms. Output impedance is low, around 50 to 100 ohms. The bandwidth is limited, so the gain will decrease at high frequency. And the noise signal, you have certain noise, so non-zero noise will be there. Internal noise will be affecting the signal quality. When we talk about the voltage and the current limitations, the output voltage is limited by plus minus VCC or slightly less. And the current is limited by the power dissipation and component rating. So the current upper limit is set by how much the maximum power the device can dissipate so that the heat is not produced and damage the equipment. So when we talk about the internal structure of an op-amp, these basically composed of three main stages. The first stage is the differential amplifier. The second one is the voltage amplifier. And the third one is the push-pull amplifier. So the differential input stage of the amplifier is the input stage. It amplifies the difference between the input. So whatever the input we are giving as the differential between the positive and negative terminal of these input stage amplifier, it get amplifies. In the second stage, we have voltage amplifier, which is the class A amplifier, as we have discussed in the previous lectures. It provides additional gain. In the third stage, we have push-pull amplifier, which are class B. This is also discussed for efficient power delivery. So we will be getting the voltage output, and these three will form the internal stages or the block diagram of an op-amp. The input signal modes and configuration, we have two input modes. One is the differential mode, and the second one is basically the common mode. In the differential mode, we have single-ended, double-ended, or the output is amplifying the difference between the input. What do you understand by single-ended? One input will be grounded and the signal on the other end we will be giving. So if we see here, the inverting and non-inverting terminal of this op-amp, one of the end is basically grounded. So this is inverting input signal. If we take the negative to be grounded, this is non-inverting input signal, which will be given to the other terminal, whether it is inverting or non-inverting. So this supply V in is basically given to one of the terminal, other terminal is grounded. So we say that to be inverting input or non-inverting input. And these are single-ended differential mode. In the double-ended, you have two out-of-phase signals applied. So both negative and positive, you will be giving a supply. So the differential voltage will be given to the input terminal, and this can also be represented as single input, which is connected with the input terminal inverting and the non-inverting, and you'll get the output. So this is double-ended differential mode. So output amplifies the difference between the input. So whatever the input we give, the output that we get is basically the amplification of the input. In the common mode configuration, you have the same signal in terms of phase, frequency, and amplitude on both the input. So we are giving the input at both inverting and non-inverting, and these are having same frequency, phase, and amplitude. So ideally, we say that whatever the output we are getting is zero due to common mode rejection. So this is known as common mode input characteristic or common mode rejection, where the output is zero. Some of the key op-amp parameters are basically the common mode rejection ratio CMMRR. These measure the ability to reject the common mode signal. So common mode rejection ratio is basically the ratio of the gain under open loop condition and the common mode condition. So the ratio of the gain AOL, which is the gain under open loop, by the gain under common mode. And since we represent this CMRR, common mode rejection ratio, in dB, so we multiply that with 20 log. So 20 log of the CMRR will give you CMRR in dB. The open loop voltage gain typically lies in the range of 10 to the power 5 to 10 to the power 6, which is quite high. Maximum output voltage swing you will be getting and limited by the supply voltage plus minus VCC. The offset voltage at the input is small DC voltage which is needed to zero the output, typically less than minus 2 millivolt. So you need to give a small amount of DC voltage. If you do not give this small amount of DC voltage, which is known as the offset voltage at the input, then it will not make the output to be zero. And this voltage is very, very less than 2 millivolt. When we talk about the input impedance of the op-amp, there are two basic ways to specify that. First, in the form of differential, and second, in the form of common mode. So when we talk about the differential, it is the resistance which is measured between the inverting and non-inverting input. So this is your inverting and this is your non-inverting input. We try to measure this resistance in the differential input impedance, and this measured by change in bias current versus differential input voltage. So whatever the input we are giving here, which is differential, so whatever the current is flowing, the ratio of that will give you the input impedance under the differential condition. The common mode condition, you have the resistance which is between each input and the ground. So you have been connected a ground at the center of a resistor. Two resistors are there which is center tapped, and you give the input. So the measured by change in the bias current versus common mode input voltage. So the input that you give here connecting the common mode configuration, the impedance that we measure at the input is known as the common mode input impedance. Output impedance is the resistance which is viewed from the output terminal of the op-amp. So at the output terminal, when we see the impedance and measure it, that is known as the output impedance. Now we have the concept of bias current. So when we have given the input, which is differential input in the inverting and non-inverting terminal of the op-amp, then the current will flow I1 and I2 in the inverting and non-inverting terminals. So the bias current is the average of that, I1 plus I2 divided by 2. Whereas the offset current is the difference of the two current, I1 minus I2, with a mod indicating that we are taking only the positive value of the offset current. So if we want to measure the offset voltage, which is developed by these input offset current, then the offset voltage is from Ohm's law, the difference of the current I1 minus I2 and whatever the input impedance you have at the Rin. So IOS, that is the offset current multiplied with the input resistance. And the error at the output that you get is basically multiplied this voltage, offset voltage multiplied with the voltage gain AV. There is a term which is very important in op-amp. This is known as slew rate. So what is slew rate? It is basically the maximum rate of change of the output voltage in response to the step input. So input that you give is basically step. So we know this is the step input, and the output voltage we need to measure as the rate of change. So voltage by microsecond will be the unit. So slew rate is nothing but the change in the output voltage with respect to the change in the time, that is the rate of change, and the input that we give is in the form of step input to the op-amp. So when we give this step input, then what is the change of the output voltage from, you can see here, from plus Vmax to minus Vmax? This change in the voltage is known as the slew rate with respect to the time delta t. So slew rate is the measured in volt per microsecond because the time is very fast. What is the meaning of noise in op-amp or any electronic devices? It is basically the unwanted signals which is affecting the signal quality. So there is certain amount of voltage which is in the form of noise. It is corrupting the fundamental frequency signal, that is known as noise. The type of the noise, if you have, then a color is associated with that. One is pink noise, another is white noise. So First, if you see the white noise, it is constant across higher frequency. So white noise magnitude do not change with frequency. It is constant. Pink noise is dominant only at the low frequency and it is 1 by f. So inversely proportional to the frequency. So when we measured this noise voltage density, the voltage measured with respect to the frequency under root hertz. Now here if you see the frequency, if you divide this low frequency and high frequency, at the low frequency, the frequency response is 1 by f and then it becomes constant, which is the white noise region. So this is the pink noise region. One example we can take, if we find this at 1 kilohertz, a low noise op-amp may have the value 1.1 nanovolt per root hertz. So the unit that we take for measurement of the noise is nanovolt under root hertz. Now we will discuss what is negative feedback amplifier. Negative feedback, why it is necessary when you have a portion of the output fed back to the inverting input, which is out of phase with the input. So whatever the output you are having, you are feeding this back to basically the inverting terminal of the op-amp. Then it is known as negative feedback. And the voltage that you feed back from the output is out of phase with respect to the input. This will reduce the gain but improve the stability bandwidth and input-output impedance control will be achieved. So negative feedback is one of the important op-amp circuit configuration where the output is connected to the input and basically it is connecting at the inverting input. So this is out of phase with respect to input. Although the gain will be reduced, but the stability bandwidth and the impedance control can be achieved. Why we use negative feedback? Let us take an example. Without the feedback, the gain will be very high under open loop condition. Here you can see that it is around 10 lakhs, which drive the op-amp into saturation. So op-amp will be going into saturation because the voltage gain is very high. And this will be limited to comparator application. We will see what is the comparator in the next lecture. But yes, the op-amp will be used for the comparator when the gain is very high. Now, when we use this feedback, the closed loop gain becomes stable and it is controlled. The bandwidth is increased and you need to have proper adjustment of the input-output impedance. So if you compare the open loop with the closed loop, parameters like gain, input impedance, output impedance, and bandwidth, we see that the open loop, although it has high gain, but that can be controlled using the closed loop. Input impedance is high and output impedance is low, bandwidth is narrower in case of open loop. However, you can adjust this input impedance, make the output impedance to be low and wider bandwidth with respect to closed loop or negative feedback configuration. The other type of amplifier configuration is the non-inverting amplifier. Here, the input is applied to the non-inverting terminal. So here you can see the positive terminal, which is the non-inverting terminal. There you are connecting this input voltage. So it is known as the non-inverting amplifier. The feedback is given through resistor Ri and Rf. So two resistors are connected as voltage divider biasing and the output voltage is given to the input with respect to these amplifiers and this is the feedback circuit. So the closed loop gain under non-inverting configuration is 1 plus Rf by Ri. You can derive this with respect to the voltage division rule. So the voltage Vf feedback is basically depend upon the output voltage with a multiplication factor Ri by Ri plus Rf. So this is with respect to the voltage division rule. Note here, this factor is known as the attenuation. So Ri by Ri plus Rf is basically the attenuation denoted by B and the differential input is basically the difference between the input voltage and the feedback voltage. So this is the differential input that we give. The other configuration, which is special case of the non-inverting amplifier, is the voltage follower. Here, all the output will be fed back to the input. So the attenuation is 1. So the output you are giving to the input without having any register. So all the output is going to the input, and hence it is known as voltage follower. This is a special case. The gain of this voltage follower is 1. The features of voltage follower, you have very high input impedance, very low output impedance, and it is idle buffer for impedance matching. So such type of application where impedance matching is required, we go with the voltage follower circuit. Inverting amplifier, you will be giving the input to the inverting terminal via the resistor Ri. So here you have the input V in. It is given to the inverting terminal minus with respect to a resistor Ri. Non-inverting input is grounded. So the positive terminal of the input is basically connected to the ground, 0 volt. The feedback is given through the resistor RF. So output voltage will be given to the input, that is the inverting terminal, through the resistor RF. Hence, the closed loop gain is equal to minus RF by Ri. Note here, this negative sign is indicating the phase inversion. So whatever the output signal you are getting, it will be opposite phase at the input because of this negative sign. Non-inverting amplifier impedance, if you want to measure, then input impedance under non-inverting condition will be equal to 1 plus open loop gain multiplied with attenuation, and it is multiplied with the input impedance. So it is greatly increased by the feedback. So due to this feedback, you can see that the input impedance is increasing. Output impedance is given by this ratio, actual output impedance divided by 1 plus open loop gain multiplied with the attenuation factor. So since this will bring down the output impedance, so it is significantly reduced. The feedback attenuation factor, again, D is Ri plus Rf. So the input and output impedance we can see for the non-inverting amplifier. So here the input is given to the non-inverting positive terminal and the output is feedback to the input with Vf, and here we have the attenuation Ri plus Rf for the input, and the output impedance we can measure with respect to output voltage by input voltage using this ratio. If we want to compute the impedance for the voltage follower, which is a special case, so the B will be equal to 1, that is attenuation factor, and hence the same formula whatever we have used earlier, with substituting the B to be 1, we will get the input impedance and the output impedance under voltage follower circuit, which will be higher than the non-inverting amplifier and low idle for the buffering. So as compared to the non-inverting, the voltage follower impedance for the input will be high and extremely low for the output. So it will be used for the buffering. When we talk about the inverting amplifier impedance, so the input impedance is approximately equal to the input Ri register. So this is Ri register, and it will determined by the register due to the virtual ground. So this terminal is basically the virtual ground, and the output impedance we will be computing similar to the non-inverting, which will be very low. So this is for the inverting amplifier input and output impedance. What is the effect of the input bias current? So we have seen the current at the terminal inverting and non-inverting, which are known as the bias current. If a small amount of this current will cause the output error voltage. So if you have the bias current, the output will be produced an error. For the inverting amplifier, this output is I1 into Rf. For the voltage follower, the output error is minus I1 into Rs. So here you can see the circuit for the inverting amplifier and the voltage follower. So the current I1, which is the bias current, and the feedback resistor Rf will be introducing an error I1 into Rf at the output for the inverting amplifier, and minus I1 into Rs will be produce an error at the voltage follower. we need to compensate this bias current. So for the voltage follower, this is done by adding a resistor R equal to RS in the feedback path. So in the voltage follower circuit, if in the feedback, if you add RF equal to RS, then in that case, the output will be 0 volt because it will be compensated with respect to the offset current IOS into RS. In the case of non-inverting or inverting amplifier, this is compensated with respect to a resistor RC, which is parallel combination of RI and RF. So we are connecting a resistor RC at the non-inverting terminal, which is the parallel combination of the input resistor and the feedback resistor. So this will produce the compensation and the output will be 0 volt and no error will be introduced. Offset voltage input, if we try, then the small DC output error will be there due to the internal transistor mismatch. So if there is a mismatch for the transistor, then also the output error will be there, which is the closed loop gain multiplied with the input offset voltage. So the compensation in this case, we use external potentiometer. For example, 741 op-amp offset null pins can be used for connecting this external potentiometer. So any mismatch or due to the offset will produce an error at the output, and this need to be compensated. Now, next topic, we'll take the frequency response. Let us see the open loop. In the previous lecture, we have discussed very detailed in the frequency response of the amplifier, and we have introduced this concept of mid-range gain, which is the maximum one, and it is a reference. So this is constant from DC, which is, so DC is 0 Hz, and to certain critical frequency, which is open loop. So let us take this critical frequency here, which is 10 Hz. So the mid-range, this will be constant. Then it will be rolling off at minus 20 decibel per decade. So this will fall up minus 20 decibel per decade till the critical frequency upper limit, and you will be getting the unity gain width product FT, where the frequency will be such that the open loop gain will be unity. So you will get unity gain bandwidth product. Phase response in this case, since we have a RC network, which is a lagging circuit, it will cause a phase shift minus tan inverse of F by FC. Phase lag will increase with frequency, and this will approach to minus 90 degree per stage. So you have multiple stages of op-amp, which is known as the multi-stage op-amp. Total phase lag will be sum which is contributing from each stage. So whenever you give the input which is sinusoidal, since you have a RC network, you will be having the phase lag at the output. Now let us see the closed loop frequency response. So for the negative feedback, it will increase the bandwidth, because the bandwidth under closed loop condition is, this is a scaling factor K multiplied with the bandwidth under open loop condition, which is 1 plus the attenuation factor B, open loop gain in the mid frequency range, and the gain bandwidth product for the closed loop and the open loop is equal, which is equal to FT. So higher gain will reduce the bandwidth and vice versa. So this part, whatever you are getting, is for the open loop in the mid frequency and then the high frequency. And here you will be getting for the closed loop. So what happened is that if you see and compare for the open loop and the closed loop, for the closed loop, the gain reduces, and this has reduces the bandwidth and vice versa. How do you select the op-amp? So we need to select the op-amp based on certain key parameters, which we have seen: the gain, bandwidth, common mode rejection ratio, the noise, what are the input and output impedance, slew rate, the offset voltage, and the current. So these are need to be checked for a particular op-amp to be selected for a particular application, and this will be available in the datasheet. The features will be short circuit protection, no latch up, and offset nulling. So we have to properly choose the op-amp for a particular application by seeing the datasheet. Application of op-amp, we use it in amplifiers, filters, we use in oscillators, analog computing, and signal conditioning. So when we use in amplifiers, we can be having inverting, non-inverting, or voltage follower circuit. Filters, we can have active low pass, high pass, or band pass filter. Oscillators, we can have sine wave, square wave generators. Computing, we can have integrator or differentiator. And signal conditioning, we can have buffering or impedance matching. This we will discuss very detailed in the coming lectures, the application of op-amp and the various circuit. Let us summarize what we have studied in this lecture. So op-amp are very versatile. It has high gain amplifier with the differential input. The ideal versus practical characteristic will guide the circuit design. Negative feedback will stabilize the gain, increase the bandwidth, and control the impedance. Configuration, when we talk about, then we have non-inverting, inverting, and voltage follower. The parameters which are of interest: common mode rejection ratio, slew rate, noise, and the voltage and current offset. Frequency response and phase shift are critical for high frequency applications, and wide range of applications are there in analog electronics. So we have discussed the basic fundamental of op-amp and their configurations. In the next lecture, we will see the op-amp circuits and their uses. Thank you for now.